trouble. So real thermodynamics potential energy in bracelets is analogous to chemical potential energy in molecules. I've been talking like that, but to be really clear about that. And that is measured in real life in what's called Gibbs free energy, called G. And if you have a reaction, so suppose you have a reaction A going to B. This is called reactant, and this is called product. Right? If delta G is negative for that reaction, then that means A to B is favored and B to A is unfavored. So we'd say the snapping of the snap bracelet has a negative delta G. If delta G is positive for that reaction, then you'd say A to B is unfavored. And the reverse is true, that B to A is favored. And finally, if delta G is 0 for that reaction, for any reaction you like, then A to B and B to A are equally favored. Something in balance, like a seesaw. Two people of equal weight on a seesaw. They're going to be, it's equally favored which one's going to go, which one's going to go down. So delta G is a way of expressing this. We're going to talk about lots of reactions with delta G. So if I tell you a reaction has a negative delta G, it's favored. It will happen. I can't tell you how fast, but it's going to happen. It's spontaneous. Delta G negative is for T, there's a reaction, the delta G for TNT exploding is negative. High potential energy to low potential energy. The delta G for me lifting this up is positive, right? And I have to put energy in to have that happen. And we'll do lots of various delta G things as time passes. So let me, I want to give an example. Rusting metal. All right, you all have, many of you have cars or have seen cars, and they tend to rust around here. This is a chemical reaction. And it's going to be not balanced. So the chemist would have a fit about this. I just want to keep the big picture and not worrying about the fine details. Is the reactants are Fe, which is iron, like the iron in your car, plus oxygen in the air, reacts to form the products. And those are Fe2O3, which is red rust. Right? And this occurs spontaneously. Right? That is, your car just sits there and it rusts. That means delta G is negative. That is, the favored reaction is iron rusting. You sit there, your car will rust. Okay? The hotter it is, the faster it rusts, but it's going to rust on you. Yes? We're not going to talk about catalysts right now. It will eventually, that is, if you leave it long enough, your car will rust. And the hotter you heat it, the faster it rusts. So delta G is negative. In fact, it turns out to be is negative 200 kilocalories per mole. What that means is this here is it's a negative sign. That's what's important. And these are the units. We won't worry about what that means, but that's how it's measured. You'll see things like measured in that way. So what this means, if you drew one of those energy diagrams, just have a little more space. One of those energy diagrams with G from high to low. Fe, iron and oxygen, your nice brand new car in the atmosphere, is up high energy, and down at lower energy, is Fe2O3, your rusted car. And the pathway, energy pathway, looks something like this. There's some activation energy. It's not 0 because it happens slowly at room temperature. Therefore, the EA must be... All right, so there's a little bit of the conclusion that I'm drawing here is the following. Because my car does not rust immediately, that means that it takes some amount of energy to get that reaction started, to get those molecules to react. And so there's some activation energy. You've got to... And at room temperature, only a small number of the iron atoms in your car and oxygen molecules have enough energy to react. So they react slowly, gradually, atom by atom, your car rusts away. If you heat it, like if you look at your muffler, which runs a lot hotter than the rest of your car, it rusts much faster because more molecules have enough energy to react. Okay? So that's the sort of a translation of a real-world thing into a diagram like that. Questions about that diagram before we go even a step further? Yeah? So if the activation energy was 0, that would mean no blip there. Would that mean that rust would turn into iron? No. It would mean your car would rust instantly, right? So that, and you still couldn't get your rust, still couldn't heat your car up and unrustify it. But what it would mean if that activation energy were 0 is that, boom, as soon as it came out of the shop, well, as soon as they came off the rolling mill, it would rust right away, right? Right. Other questions? That was a good one. Other questions? Is that yours too? Okay. Yeah. If the overall energy was 0, then it would be equally likely to rust and unrust. So that basically your car would sort of reach some mid-level of rust and stop. Would be more or less what it would do. What this says, eventually your entire car will rust. Right there, you would reach an equilibrium of sort of partial rust if the overall energy was 0. Other questions? Yeah. How can you make it unrust? You actually have to put chemical energy in, and they do that at an iron smelting plant with, I think you actually burn, I better not say, but it's complicated. But you have to put chemical energy in, basically. All right, let me add one last wrinkle, and then we'll call it a day. So there's a couple rules for delta G. One is that the reverse reaction has reverse sign of delta G. So that is Fe2O3 going to Fe and oxygen. The delta G is positive 200 kcal per mole. Right? So you can use them sort of algebraically. And delta G's can be added. Right? So, for example, I guess if I find a bit more space, if you have iron plus oxygen goes to red rust, Fe2O3. That has a delta G of minus 200. It's also true that Fe2O3 plus some more oxygen, you can further oxidize the iron and get Fe3O4, which is black rust. And the delta G for that is about minus 70. You can add them up, and you can get Fe plus oxygen plus Fe2O3 plus some more oxygen goes to Fe2O3 plus Fe3O4, blah. You basically can add them all up, and you can cancel terms. So what you get is iron plus a lot of oxygen goes to the iron Fe3O4, and its delta G is minus 270. Okay, you can add them up like that. Sort of like some simple math. And so you might ask, doesn't my car rust black? Right? Because we're saying rusting all the way to black rust. I don't know if you've ever seen hematite. It's this really nice black, shiny mineral. I've used it for jewelry sometimes. Sometimes it's magnetic. It's black and shiny and rather pretty. That's black iron oxide. Why doesn't your car rust black? And it turns out the answer to that is if you waited long enough, it might. But the thing is that the Fe2O3 plus oxygen going to the Fe3O4 has a very high activation energy. Therefore, it's very slow at room temperature. All right, so you have to get it really, really hot to have that happen at any appreciable rate. Okay. So, but you can do these math kinds of things like that. Questions about that before we do the eye clicker question? Yeah. Why doesn't what? So why doesn't rust when it's quicker when it's colder? Oh, so like it seems like in the winter it rusts more. That's actually because road salt accelerates the process. And yeah, so it's the accident of it rusting more in the winter is actually not because it's colder. There's other factors. You're right. I told you a simplified story. Yeah. Why does what? Why does water help? Because of the particular mechanism of the reaction. I better not. I can talk to you after. But there's an interesting answer, but not a simple one. All right. Let me do the clicker question, and we will call it a day. Yeah. Oh, hey, everybody. Let me do this one thing. The higher the activation energy, the slower or the faster the reaction. Higher activation energy is going to make it slower because fewer molecules can make it over the bump. So higher activation energy means slower reaction. That's an important question. All right, let me do the clicker. All right.